Hello everyone, I'm Gilles Pesan from Polytechnique Montreal in Canada. This is joint work with Bérouz Webeki, doing a postdoc with me in Montreal, and Claude Guy-Quimper from Laval University. So this talk is about solving some AI planning problems using a standard constraint programming approach with nothing specific to planning, and in particular how some generic combinatorial search heuristics developed for CP are key here for our approach to be effective. So I'll first give you a quick background on AI planning, on constraint programming. Then we'll see, using a well-known planning domain, how one can model it in CP. Then how we explore the search space defined by that model. We'll have a look at some experimental results and conclude with some remarks. So, some background. So we're interested in classical AI planning problems. Well-known example is blocks world. So you have a number of blocks here, A, B, C, set on a table in a certain configuration. You have an initial state of the world, shown here on the left, and you want to reach your goal state, so another arrangement of the blocks shown on the right. To reach that goal, you have some actions that you can perform on those objects. So you can stack or unstack blocks, or pick them up from the table, or put them down on the table. You don't know how many actions you'll need to execute that plan, how many steps there are. And in the planning community, they're interested in designing domain-independent planners. That is a planner that will be just as good for blocks world as any other planning problem, so nothing specific to the blocks world problem. And in our case, we can see what we're proposing as a planning-independent approach. So we're using some out-of-the-box CP constructs to solve planning problems. There's nothing specifically developed for planning. How about constraint programming? So you model your problem, you define some variables, each taking its value from a finite domain of values. On those variables, you impose some constraints, and CP has a rich set of constraints beyond just arithmetic constraints, for example. And behind each constraint, there are sophisticated inference algorithms to help you solve the problem. You solve a combinatorial problem by tree search. At each search tree node, you perform some domain filtering. That is, you remove from the domain of variables values that cannot possibly lead to solution. And of course, you branch as well. And the effectiveness of your approach can be quite dependent in general on the quality of your model and the quality of your branching heuristic. So you have to write good models and use good branching heuristics to solve your problem. Among those, that rich set of constraints that CP provides, one that will be very useful here is the regular constraint. So it's based on automata. So given a sequence of variables x1 to xk and an automata A, it will impose that the sequence of values taken by those variables spells out a word that is recognized by the automaton. And there's a cost variant of that constraint, cost regular, where you're associating costs to each transition of your automaton. Cost variable z is equal to the sum of those costs. So using CP for AI planning is not new. Typically, you fix the plan length and look for plans of that length. You use constraints such as regular. As early as 2006, there's been proposals for that. But typically, you use simple combinatorial search heuristics. So what's new here? We use the cost version of regular as well. For a given planning object, we will map the set of all actions to a reduced set that are relevant to that object. We'll see an example of that soon. And especially, so we will be using combinatorial search heuristics that are much more effective while still being planning independent. So again, our aim here is just to use good old CP, nothing specific to AI planning. So how do we model a classical AI planning problem in CP? Consider the well-known floor tile planning problem. So you have a tiled floor. Some of those tiles need to be painted of a particular color. And you have a set of robots on that floor. They can move around, they can paint tiles, and they can change the color that they use to paint the tiles. So here you have 15 tiles. The dots on some of the tiles indicate the color that you need to paint them. And you see two robots whose color indicates the color they hold. The actions have different costs. And so here the planning objects whose state is affected by the actions are the robots and the tiles. So the first step is to define the variables of our CP model. We simply define one variable per plan step. Each variable takes its value from this set of all possible actions. There are quite a few here. So there are as many as the number of robots times number of colors plus 6 times the number of tiles. Second step, we need to add constraints to our problem. So for each planning object, we define the action mapping and a constraint to indicate which action is possible given the current state of the world and how that state is changed by the action. For example, for each tile, here's the tile automaton. So for a given tile, there are only 3 states. It is clear, occupied, or painted. And we dramatically reduce the number of relevant actions here. We can move to a tile, move away from it, you can paint it, and all other actions are irrelevant to that tile and are mapped to an other action. And we post a regular constraint on this sequence of variables using that automaton. For each robot, I'm not expecting you to read that automaton. It's quite larger and actually just part of it here. The states represent where the robot is at a given point and the color it's holding. We still map to relevant actions, but there are still quite a few. So basically the irrelevant ones for a given robot are the actions about the other robots. So we map set of all actions to that reduced set, and we use here a cost regular version. So we use the automaton to specify which actions are possible given the current state, but also include the cost of these actions on the transitions in the automaton. And there's a variable z sub r for robot r that represents the sum of these costs. Finally, step 3, you define the objective you want to minimize. Here we want to minimize the cost of the plan, so we minimize the sum over all robots of those z sub r variables. So collectively, the automata for planning objects provide a factored representation of the world. Consider, for example, the partial current state where robot R is on tile T with paint color white. You've got 3 automata represented here, one for tile T prime, which lies above tile T. So that's you have left below the automaton for tile T, and on the right, the automaton for robot R. In green, you have the current state of each planning object. So T prime is clear, T is occupied, and robot is at location T with holding color white. Suppose we're considering next action being moving up, so robot R moving up to T prime. That can only take place if that action is valid in every automaton. So it corresponds to a move to for tile T prime, a move away from for tile T, and a move up for the robot automaton. Those are the orange actions, and then you move to these current states. And then if you want to apply paint down, so the robot R painting the tile below, tile T, that's a no up, that's an other action for T prime. Tile T moves to painted, and these are the current states. But what's really going on inside each of these regular constraints here? Well, the automaton is used to build a layer graph. You basically unfold the automaton into as many layers as there are steps in the fixed length plan that you're considering. So here would be for automaton T. So that's what we've done here. And but because it needs to finish for a valid plan to be, that tile T needs to be painted, in the last layer only the painted state is valid. The others will not correspond to a valid plan from the perspective that tile T. So we can clean up, and that's what happens in those regular constraints. Now, this is not something that's going on particularly for planning. It's just in general what the algorithm does inside that constraint. And now every arc left belongs to a valid solution to that constraint. In fact, every path from the first layer to the last layer is in one-to-one correspondence with a valid solution to the constraint. From this, what can we get? We can do some domain filtering that I mentioned before. So for example, we see that because in the second to last layer of actions, there's no move to action, that can be filtered out of the domain of possible actions in the third step of that plan. And in fact, we see that it makes sense. You can't, if you're moving to tile T, then you can't possibly paint it in the next step. So now how do we search over the combinatorial space that's been defined by our CP model for our AI planning problem? So as I said before, we're solving fixed length plans. We do something very simple. We solve models of increasing length. So we start from some trivial, really, lower bound L min. As I said, we don't want to inject really any smart planning knowledge about the lower bound on plan length. We stop looking for plans of increasing length once we've established that there cannot be better ones further down. And when we solve our model for a given length L, we also include a timeout to possibly interrupt and move on to the next length. So what are those combinatorial search heuristics that really make a difference here? They're based on counting solutions. So here again is the layered graph that we maintain for each regular constraint. And we can also store some information about the number of incoming paths and number of outgoing paths in each node. That's what you're seeing here. And that information is being used to choose the next variable to fix, to branch on, and the value to give to it. Just to give you a bit of an idea, so for example, if we look at the red arc here, that corresponds to a move from action, and the second step of our plan. We can multiply the number of incoming paths, this is 1 here, to the number of outgoing paths, 2. So to get that there are 2 solutions here in that to that constraint that use the move from action step 2. And you can observe from that information that a move from action as a second action is twice as frequent as a move to or paint action in valid plans with respect to that particular regular constraint. So you use that frequency information to decide what to branch on. And what we've observed is that this tends to correspond to making smart choices of actions to try first. For example, in the floortile planning domain, it could correspond to painting the tile currently above a robot if he's got the right color and he's in the right place. Or moving one robot out of the way before having another paint a tile. So all these actions make sense and they're selected as actions to try first automatically. And that's what we find quite interesting, without any planning knowledge being added here. I'll refer you to the paper for the experimental results on 3 different planning domains. But to summarize them, in the first experiment, we confirmed that counting-based search finds plans for many more instances than other common search heuristics in CP. And in the second experiment, we showed that on some planning domains, we can produce plans which are comparable to those from the state-of-the-art planner fast downward stone soup. So to conclude, I think the takeaway message is that you can build an effective CP approach to classical AI problems without injecting planning knowledge. What really makes a difference and here is using counting-based search as a combinatorial search heuristic. We observe that most of the computation time is wasted looking for plans at infeasible plan lengths, and that once we're at a feasible plan length, often very, very quickly we find a good plan. So we'd like to, as follow-up work, really look into counting-based search for planning, analyze more deeply its behavior and seeing how it relates to existing planning heuristics. We'd like to see how our approach performs if instead we start with a good heuristic to find a feasible plan length, and having an alternative modeling language for AI planning in terms of automata and action mappings would make it much easier to apply CP to such problems. Thank you.